Hi everybody. In this video, we're going to be finding the unsigned or absolute area of a region bounded by graphs of functions. So here's the plan. We'll use integration to find area between graphs. And before we do that, we're going to review the definition of definite integral. And we're going to visualize Riemann sums as pre-integrals. So we're going to imagine diagrams that look like this as a vehicle for helping us set up directly the appropriate integrals that will help us find these areas we're interested in. And we'll work out two examples. So here's a nice continuous function on the interval from 0 to 7, and we could divide up this interval into 7 equal pieces and choose, say, the midpoints to use as so-called sampling arguments and evaluate the function, calculate areas using those function values, and that would be a midpoint sum with 7 divisions. And you could increase the number of divisions. This is, you increase the number of divisions, you presumably get a better and better approximation for the area. And indeed, the definite integral is defined to be the limiting value of such Riemann sums. And this is our definition of the definite integral. And these Riemann sums can be, you have many options. They could be midpoint sums, left-hand sums, right-hand sums, or there are many other types of appropriate sequences of Riemann sums that allow you to calculate the integral as a limiting value of such sums. But here's what we're interested in this video. We want to remember that the definite integral yields signed area. So these function values, whether they're positive or negative, will contribute accordingly to the sum of the areas. So the boxes that lie below are counted negatively. So in the end, this integral will actually measure signed area between the graph of f and the horizontal axis. So this region would count positively, and then the area of this region would count negatively. So in this particular example, we wouldn't even need to invoke any kind of limiting value of Riemann sums or the fundamental theorem. We can actually look at this graph. We know how to calculate these areas, so we know that this triangle and this quarter circle, we know how to calculate those areas, so we could calculate directly the integral value. In this case would be 9 pi over 4 minus 4. So now let's talk about the absolute area bounded by graphs. Suppose you have some shape in the plane, and you're actually interested in finding its good old-fashioned area. So in this context, we use area to mean unsigned area, or what we might call physical area, or absolute area. It's the kind of area you're interested in if you're a painter. I mean, you look at this shape and you say, well, how much painting do I need to do? If you're going to paint this, you don't really care whether the region lies above or below the x-axis. You're just interested in knowing how much paint do I need to apply. That's what we mean going forward by absolute area. We just mean a good old-fashioned quantity that tells you the amount of area. It's a positive number, and so we don't care whether something lies above or below the axis. We'll start with this example. Suppose we have graphs of two functions, f and g, and the graph of f lies completely above the graph of g, and we want to find the area under the graph of f, above the graph of g, and between the arguments a and b. We can picture this pretty well. We know that the integral of f from a to b should give us this area, and we know that the integral of g from a to b should give us this area, and we're interested in the difference. So in this case, it's pretty clear that the area should simply be the integral of f minus the integral of g. But we're going to do something with this formula. We're going to recall there's a property of integration which says that if you integrate the difference of two functions on an interval, you can actually decompose it into the difference of the integrals. In our case, what we'll do is we'll reconstitute this. We'll take these two different integrals, since we're taking a difference, and we can rewrite it as a single integral of the difference. So the area in this case is given by the integral of the difference of f and g integrated on the interval from a to b. Consider now an example where the graph of f is still lying above the graph of g, but now both the graph of f and g lie below the x-axis part of the time. Now recall that we're trying to calculate absolute area. So this area we're trying to calculate here, we don't care that it dips below the x-axis. But there's this funny interaction when you try to imagine what's happening the way we did just a moment ago. Because the integral of f by itself is a signed area. So that quantity will give you a signed area. You'll have part of this lies above, part of it lies below. So you have a portion that counts positively, a portion that counts negatively. And similarly, when you integrate the function g. So you have to really do some mental gymnastics to convince yourself that the absolute area you care about is really given by the difference of these two signed areas. And so rather than try to convince yourself that this is true, which is a good exercise, you should do it, I think a better method is to imagine the difference formula directly as a calculation giving you absolute area. So how would that work? Because the graph of f lies above the graph of g, we know that f of x is greater than g of x for all x in this interval. And that means the function f of x minus g of x is going to be a positive function on this interval. So we can imagine that the graph of f is the top of this object and the graph of g is the bottom of this object. And we can imagine approximating the absolute area as the sum of the areas of these rectangles right here. Now the connection between these two sides of this slide here is that the heights of these rectangles are given by this function f of x minus g of x. So we can think of this as being a height function for these rectangles. And so if we wanted to approximate the area as a sum of areas of rectangles, we'd get an expression that looks something like this, where delta x is the common width of these rectangles. And that height function being f of x minus g of x, we'd get this expression here for our approximation to area. But what does that look like? It's a Riemann sum. And if we let the divisions get finer and finer, we know that in the limiting value, we'd get this integral right here. So what did we get? We get that the absolute area is, in fact, the integral over the interval from a to b of the top function f minus the bottom function g. In other words, the formula that we derived so easily a moment ago in the simple example turns out to be the case even when your region dips below the x-axis. So this little game takes into account signed areas in a way that allows you not to have to worry about it. If you take the top minus the bottom and integrate, you'll get the absolute area. So let's look at an explicit example. Let's find the exact absolute area enclosed between the graphs of f and g, as stated here, and between the lines x equals -1 and x equals 3. So the graph of f is a parabola, and the graph of g is a shifted exponential function. And the region whose area we're trying to calculate looks like this. Once again, you have some of this region lying below the x-axis, but our method is going to take that into account, no problem. So I would suggest visualizing first a Riemann sum. So we're going to be approximating the area with rectangles that might look like this, and that'll help you imagine the height function. So the height function can be obtained by taking the top minus the bottom. F serves as the top of our region. G serves as the bottom of our region. So our height function should be f of x minus g of x. And if we plug in explicitly what that means, we get an explicit height function that looks like this. We can simplify that, and so now we have the height function. We're going to set that aside. Let's think about what our Riemann sum looks like. We'll have a common delta x. And by the way, the delta x should tell you, that's a tip-off, that we're integrating with respect to x. We're going to add these boxes up along the horizon, and that means we're actually shooting for an integral with respect to the variable x. Now we can imagine putting in sampling arguments and getting an actual Riemann sum, but it's not so important to write that down so much as just to imagine where that puts us when we take the limiting value. You can hopefully picture that this leads to an integral from -1 to 3 of your height function with respect to x. Now let's evaluate the integral exactly. This is a pretty reasonable antiderivative to find, and you can plug in the endpoints and subtract, simplify. You get this as your exact area, which is what was requested, and you can evaluate this on a calculator and find that it's about 4.832, and this is reasonable if you just count some squares. Here is a region whose area is 5, so we can see that we're in the right ballpark. So this seems to be a reasonable calculation, and we have found the absolute area of this region. So where does this go generally? I'm going to introduce the variable zeta for a couple of reasons. One is you should be flexible with your variable of integration. Ultimately, your variable of integration does not matter. You could call it whatever you want. It's a placeholder, really. And in a moment, you'll see another very good reason why I'm not using x here. So here could be your approximation of the area using rectangles. And just imagining one rectangle is enough to realize that your height function here will be a function of zeta, and your top function and bottom functions will also be functions of zeta. Here's your width, and then you want to integrate from the smallest value of zeta in your picture to the largest value of zeta. So you can get a sort of generic formula that looks like this. And if you want to break it down a little bit, you can say, well, the height is the top minus the bottom. So this is how you find the area. And you'll notice that everything in this expression has to do with the integration variable zeta. Your limits of integration, the functions themselves are expressed as functions of zeta, and then, of course, the differential itself. So once you've identified your integration variable, you should take that as a cue to express everything in terms of that variable. Now what we're going to do is we're going to flip this picture across the line y equals x. And the reason we're going to do this is we want to have the flexibility to integrate with respect to the vertical direction. So now zeta is essentially the y variable, but the formula still holds. The idea is that when you want to find an area, once you've identified your integration variable, everything in your integral needs to be expressed in terms of that variable. Please notice in this diagram the direction in which you would move to go from the bottom to the top of your shape, and the direction in which you're integrating when you go from the smallest to the largest value of your integration variable. Let's put this all together with an explicit example. So here are two curves. One is a parabola, one is a line, and they're both graphs of these equations here, and we would like to find the absolute area of this region trapped in between. But we're going to do it two ways. We're going to do it first by integrating with respect to x, and then we're going to integrate with respect to y. So our first job is to find the coordinates of the two intersection points, because we're going to need limits of integration, which we don't have right at the moment. So here are our two equations. And let me just say that solving general systems of equations, unlike solving linear systems of equations, it's more of an art than a science. There isn't a pure algorithm that's always going to tell you how to proceed. In this case, you should notice a little trick here that if we multiplied the second equation by 3, you actually get a new equation that balances out the other one on the right. So we can actually subtract these. And when you subtract the right-hand side, you get 0. And on the left side, you get 4y squared minus 12y. We can factor that quantity, 4y times y minus 3 equals 0. And there you go. We've solved for y. So y is either equal to 0 or equal to 3. Now, here's our linear equation. So we can take each of these values of y. For example, y equals 0 would imply that 3x is equal to negative 6. So x is negative 2. And on the graph here, we can identify this intersection point as negative 2, 0. Similarly, when y equals 3, that implies, thanks to the linear equation, that 3x minus 12 equals negative 6. And that means that x equals 2. And so our other intersection point should be the point 2, 3. Now, here's what you should visualize when you're trying to integrate with respect to x. And so what we need to do is identify the top function as a function of x. So we need to take this equation and we need to solve for y as a function of x. Now it's almost done. All we really need to do is divide through by 4. We're going to factor out a 9 as well on the right side. And now we need to take the square root. The square root gives us two options, plus or minus. But we can see from the graph that we want the top half of this parabola, so we should take the positive root. So in fact, the equation that we need here, the expression for the top function as a function of x, is 3/2 root x plus 2. Now we need to play the same game for the bottom function. 3x minus 4y equals negative 6, and we're going to solve for y. So in this case, y equals 3/4 x plus 3/2. So that's our expression, once again, of the bottom function as a function of x. And now we're ready to apply our formula. We know that here's the generic formula. We want to go from the smallest value of x to the largest value of x, and we want to integrate the top minus the bottom as a function of x with respect to x. Well, The smallest value of x is -2, and we're going to integrate up to the largest value, which is 2. And the top function and the bottom function we've just discovered. So here's our integral. Smallest value of x, largest value of x, top minus bottom. This is our integral. We can plug this into Desmos if we want, just to get to the punchline. Apparently, this isn't so bad. You could use the fundamental theorem and evaluate this by hand. It's a good exercise, and you should get 2. So the area enclosed here, the absolute area we're looking for, is 2. Now we're going to go back and repeat this calculation because we should be able to do this by integrating with respect to y. So in this case, we're going to turn our head. And we're going to notice that this, you should be able to visualize sort of how your Riemann sum might look like, and this will help guide you. And you should identify that the top function now is given by the linear graph. And the bottom function is now given by the quadratic graph. And when we integrate, we're going to integrate from our smallest value of y, which is 0, to our largest value of y, which is 3. So those are the ingredients we need to deal with. Now our integration variable is y, and so we're going to need to solve these for x as a function of y. The linear case is not so hard, so x equals 4/3 y minus 2. And then for the quadratic piece, that's not so hard either, x equals 4/9 y squared minus 2. So these are our expressions of the top function and the bottom function as a function of y. Here's our generic formula. And now we're going to put in the specifics in this case. So we're going from 0 to 3. We're integrating the top minus the bottom. So this integral should give us the area. And once again, we plug this into Desmos and we see we get agreement. We get 2. And again, this is an excellent exercise for you to use the fundamental theorem. Calculate this by hand. Really make sure that you get 2. But this is a great example of how you have the freedom to integrate either with respect to x or with respect to y to get this absolute area. In either case, you'll get 2. All right, example B. This is very similar, actually. We're going to have a parabola and a linear graph, and we're going to find the absolute area in between. This time, we'll just assert what the intersection points are. You could find those as an exercise, but we want to find this area right here. Now, we could integrate with respect to x, and this is probably what you want to do most of the time because you're so used to just using x as the independent variable. But we'll notice that there's some trouble here because this is what your Riemann sum would look like. It's good to visualize such a thing. Integration with respect to x requires 2 integrals since a transition occurs where the description at the top changes. So you can see that you can integrate only up so far until you need to switch your description of the top function. That's what's going to require 2 integrals here. Now, the top function on this side is given as 1/2 x, and the top function on this side is given as square root of 8 minus x. Good exercise to do that. Here's our bottom function, negative root 8 minus x. You have one description of the bottom throughout. Your smallest value of x is -8, and your largest value is 8. So your area is given by 2 integrals here. So we'll have to integrate from -8 to 4, top minus bottom, and then 4 to 8 with the new top minus the bottom. So the area is given by the sum of 2 integrals. Now let's repeat this. This time we'll integrate with respect to y. Your Riemann sum would look something like this. Y will be our integration variable. And you might want to turn your head to picture this, but bottom to top goes in this direction. So in this case, our top function expressed as a function of y, our integration variable, will be 8 minus y squared. And the bottom function expressed as a function of y, the integration variable, will be x equals 2y. The smallest value to the largest value, we go in this direction, so we'll be integrating from y equals -4 to y equals 2. The beautiful thing with this method is we've got just one integral that we need. We can integrate from -4 to 2, top minus bottom, which is 8 minus y squared minus 2y, and that should give us the area. Now, compare these two results. If you insist on integrating with respect to x, you get the sum of these two integrals, which it doesn't look that pretty. If you integrate with respect to y, you get a single integral that's actually not bad at all. So the point of this example is really that you should not simply go the route that you're familiar with just because you're unwilling to sort of tilt your head 90 degrees and try something new. In this case, integrating with respect to y really is a superior method because you get a simpler integral and you get one integral. In fact, we can just finish the job here by finding our antiderivative, plugging in the endpoints and subtracting, and we find that the area enclosed here is 36.